All right, and we are back with the second section in chapter 2, which is going to deal with linear inequalities in two variables. Okay, with two learning targets. The first is that you can use inequalities to solve real life problems. So that's the same as what we did in the first section. We're just going to use word problems essentially using these concepts. But the third, which is new, is that you can graph, solve, and understand solutions of inequalities in two variables. Okay, so the first thing that we're going to need to know is that a linear inequality in two variables is an inequality that can be written in the forms ax plus by is less than, greater than, less than or equal to, or greater than or equal to some letter C. So really you may recognize that this is like the standard view of linear equations or straight lines. But it also can be written in slope-intercept form as well. And you can essentially graph these lines about the same way as you could in, for example, I believe 1.1. Okay, an ordered pair, x comma y, is a solution of a linear inequality if the inequality is true when the values of x and y are substituted into the inequality. So kind of same concept. We plug in x, we plug in y. If it makes it true, it's a solution. If it makes it false, it's not a solution. Okay, the graph of the linear inequality in two variables is the graph of all solutions in the inequality. So much like in 2-1, we would get we had a number line and we would say, well, there's not just one solution, there's a whole set of solutions, like all the x values less than 5. So like 4, 3, 2, 1, 0, -1, etc., etc. Those are all solutions. Here it's kind of the same concept where it's going to be x values less than a certain value and y values greater than or less than a certain value, and them in combination to each other. Okay, and so the graph of a linear inequality in two variables is the graph of all solutions of the inequality. The boundary line of the inequality divides the coordinates into two half planes. So we'll see what half planes are because that's really what we're going to be graphing today primarily. And so we might as well just go ahead and talk about what are solutions. So what are solutions? This is just in general. This is not specific to inequalities. Solutions are, in general, values that can be replaced for the variables, and it makes the expression, or equation, inequality, whatever it may be, true. So as I look at this here, I want to know whether the ordered pair 1, 4 is going to be a solution to 2x plus y is less than 5. So really what I have to do is I'm going to take what x is equal to and replace it, and y that is what it is and replace it. So I'm going to go 2 times, but instead of x here, I'm going to put 1. And then I'm going to add to it 4 is less than y. 5 is what I meant to say. So this is going to be 5 here. And I probably should have put this 4 in red, as that's me replacing the variable. Not that it's incorrect. Okay, so then here I have 2 times 1, which is 2, plus 4. And this is going to be less than 5. And then 2 plus 4 is 6, which is less than 5 is this statement. Okay, so as I'm looking at this statement here, when I plug in 1, 4, I get 6 is less than 5. So we want to think about the truth of that statement, whether it's true or false. Well, this statement is false because 6 is not less than 5, it's greater than 5. And again, you want to really pay attention to the sign, because if it's or equal to, that might change your thoughts on whether it's true or false. Okay, so we find out that 6 is less than 5 is a false statement. So what does that mean? That means that this is not a solution, okay? So this is not a solution. Okay, so when we take our graph and we plug it into when we'll divide our graph into two half planes, what this means is this is lying outside of the half plane that we're going to identify as our solution set. Okay, so what I want you to do is pause the video and then move on to letter A, and then check your work with me. And I'm assuming that you've already done that at this point, so I'm going to go ahead and show you your work. So here I'm going to have 2 times, and then this is 2. And then I'm going to add to it. And I'm going to put in a parentheses around -1 here, just because plus minus 1 sometimes can be a little confusing. Okay, so here I get 2 times 2, which is 4. And then minus 1. Plus -1 is the same as minus 1. And so then here, 4 minus 1 is 3. So I get 3 is less than 5. Well, this is a true statement. So that means the ordered pair 2, -1 is a solution in general. Okay. So that's just kind of how we check whether an ordered pair is a solution. This will actually be pretty helpful because this will help us identify where we're going to have our half plane, like our shaded region, when we do these problems. Okay, so what I am going to do now is I am going to move on to the next 2 problems. All right, the nice thing about these problems are that they're going to have a lot of consistencies with things that you've been taught before in the past. So this will be extremely helpful if you need more assistance on graphing straight lines. And if you already know how to do this, hopefully it's a little bit of a breeze for you. So what I want to do is I want to graph 4x minus 2y is greater than or equal to 8. So you really want to try to identify which form your graph is in or your equation is in. Remember, you'll always have the option to go ahead and put it into slope-intercept form basically anytime you'd like, though you don't have to. Okay, this particular one is in a form that we call standard form. Okay, we kind of consider it in standard form when the x and the y are on the same side of the inequality sign or equal sign, depending on what you're dealing with. So when it's in this form, basically what you want to do is you want to find 2 things. The first thing you want to do is find the x-intercept, which implies that y is equal to 0. Okay, let's talk about y is equal to 0 when I'm on the x-intercept. So the x-intercept means where does it cross the x-axis? So where it crosses the x-axis is on this black bold line. It's the x-axis. Okay, well, what's the y value when you're there? So think about it doesn't matter where you're at, as you lift up or off of that line. As I lift up of that line, those y values become positive. As I dip below the line, the y values become negative. So what's that number in the middle? Well, it's 0. So whenever you're on the x-axis, your y value is 0. So I can go ahead and just solve this problem with the y value of 0. Okay. So then this becomes 4x is greater than or equal to 8. Divide by x. So that means x is greater than or equal to 2. Okay, so what does this mean? This means my graph is really just going to cross the x-axis at 2, even though we have a greater than or equal to sign. This is just where my boundary line is going to cross the x-axis. So 1, 2. Okay, so I have a dot there. That's where my graph is going to cross the x-axis. Now notice that, I didn't have to go ahead and plug this in because it's pretty elementary level math, knowing that anything times 0 is 0. So if you want to, you could completely skip this step here and just write 4x is greater than 8. And I would find that perfectly okay. And you're going to see me actually do that with the y-intercept here. Okay, so when I'm the y-intercept, so what's the information I know when I'm on the y-axis? So here, it's kind of the inverse question to this one here. As I'm on the y-axis, as I go off to the right, my x values become positive. And as I go off to the left, my y values become negative. So what's that number in between? It's 0. So here I know that my x value is going to be equal to 0. So that means I can kind of I can get rid of the x completely, and I can just write negative 2y is greater than or equal to 8. Okay, and then I just have to solve for y. So y is less than or equal to negative 4. This is just a nice reminder that you need to flip your sign when you multiply or divide by a negative. So negative 1, negative 2, negative 3, negative 4. Okay, so now what we need to talk about is that's going to be our boundary line. So when we have these graphs, they are going to have a line, and then we figure is the solutions to the left or to the right of the line. That's what we want to figure out. Okay, but you have to be careful about the line because it's not necessarily a solid line every single time. Sometimes it is a solid line, but other times we're going to have a dashed line. So right now is a perfect time to talk about the difference between the two, and it's kind of the same concept as the open circle and closed circle that we talked about in 2.1. Okay, when it's a closed dot when we're doing one variable, for example, if we look back here, when it is a closed dot, that means that 3, in this example, is included in the solution set. As opposed to when it's an open circle, that means it's not included. So this would be an example of this boundary number being inclusive in the solution set. And this is an example of the boundary number being exclusive to the solution set. That concept's true, but instead of a number, it's a set of numbers that are going to fall on a line. Okay, so it is going to be when it's inclusive, when the line is included in the solution set, it will be a bold line. Okay, and when are you going to see a bold line? You're going to see a bold line when you have greater than or equal to or less than or equal to. Exclusive is going to be dashed. Okay, and this is when it's less than or greater than. Okay, so let's look at ours. Is the line that I'm going to create be inclusive or exclusive? Hopefully you're saying that it's going to be inclusive, so the solution or points on the line will be part of the solution, and that will be because of my inequality sign is a greater than or equal to. Okay, so all I have to do is make my line. I know it's a bold line. Okay, I know it's a bold line. And then what I have to figure out from there is where are my solutions relative to this line? So this is the half plane concept that we talked about in the first part. This line just tells me that if I'm on this line, it is solutions to this inequality. But there's going to be another set of solutions. They're all going to be over here, or they're all going to be over here. Okay, and to figure out where my solutions lie, we just essentially have to test a point to figure out whether it's a solution or not a solution. Okay, so we have to test a point. Looks like I didn't give us a very good enough space to do this, but just kind of do the best that you can. B will require a little bit less work. Okay, so we have to test a point, and you can test any point you want that's not on the line. Okay, but you want to be strategic about it. Like, do I want to pick 8, -7? I could test 8, -7 and see if it works, but we want to do something that's going to require the least amount of work. So often, what's the easiest number to multiply and to add or subtract together? Hands down, that number is 0. So in general, for the easiest amount of work, we want to test 0, 0. Although you're allowed to test any other point. Okay, so I'm going to put a little x here, knowing that that's my testing point that I'm picking. Okay, and then all I have to do is plug in 0 for x and 0 for y. So I'm going to have 4 times 0 minus 2 times 0. And that's going to be greater than or equal to 8. So when I solve this, 4 times 0 is 0, minus 2 times 0 is 0. And I get 0, right? This is all 0 here. That's kind of why I picked 0, because it's just the easiest. So I figure out that this is 0 is greater than or equal to 8. So let's go ahead and just kind of think about what does that mean as far as 0, 0 being a solution. Okay, so what does that mean? It means if it's a false statement, it's not a solution. But if it's a true statement, it is a solution. So what is the ordered pair 0, 0? Is it a solution or is it not a solution? Okay, hopefully you're telling yourself that it is not a solution because this is a false statement. So how does that inform me where to shade? Do I have to go and test other points? Well, no, you don't. Because I know all my solutions are over here on this side of the line, or all my solutions are over here on this side of the line. You can't have a side that has some solutions and some not solutions. They're either all over here or they're all over here, and that's just it. So I tested a point over here, and I found out it's not a solution. So what does that mean? That means all my solutions lie opposite of that. Okay, so if I would have tested this and found this to be true, I would have shaded this side. But I didn't. I tested it. I found out it's false. That means it's the other side of the line that are all my solutions. So what I'm going to have you do is get a highlighter out and go ahead and just shade in the other side. So anything in the highlighted region or on the line is a solution to my linear inequality. And that's done. So if I wanted to ask you a question, give me an ordered pair that is a solution, you're going to pick any ordered pair on the line or any ordered pair in the shaded region. Okay, now before I ask you to do letter B, I want you to think about what form that this is in as far as graphing of straight lines. Is it in standard form or slope-intercept form? Otherwise, pause the video, move on to letter B and do it on your own. Okay, so I'm assuming that you've already done that. You've already paused the video. You've already checked, and you're just ready to check it now. Okay, so I'm looking at this, and I'm identifying this to be in slope-intercept form. Okay, and so that means I'm looking for two things, and those two things are the slope and the y-intercept. Okay, so M and B. M is my slope, and so that's the number multiplied by the x variable. So for me, this is -2. Okay, to conveniently graph, I'm going to write it as a fraction. So if it's already a fraction, leave it alone. If it's a whole number, put it over 1. And then my other value is going to be 3, the number being added or subtracted, but not being multiplied by x. So this is 3. So when I graph this, I'm going to go to the y value of 3, because this is my y-intercept. So 1, 2, 3. Put a little dot there. And then the slope of -2 is going to tell me to go down 2, right 1. So this top number is telling me down because it's negative. The bottom number is positive, so it's telling me right. So I'm going to go down 2, 1, 2, right 1. Down 2, right 1. Down 2, right 1. Okay. So just get a couple. You know, technically you only need 2, but a lot of times with slope, the points are so close together, you want a couple. Okay. So now that I kind of have the beginning of my boundary, before I make a line, I want to really make sure I know whether that this line is going to be part of the solutions or not part of the solutions. So as I look at this, I see this less than sign. And less than signs I know would be an open circle if it was one variable, but it's two variables. So I'm looking at this and I know that I'm going to have a dashed line, because it's not or equal to. So not or equal to, so that means I'm going to have a dashed line with all my points. Okay. And then what I'm going to do is I'm just going to dash these kind of dots together. Okay, and so what is this explaining to me? That means if I'm on the line, it's actually not part of the solution set. My ordered pairs, my solutions off the line on one side or the other, we'll have to figure out which one, are going to be the solutions. But if I'm on this line, it is not a solution because of the exclusive boundary. Okay, last thing I want to do is I want to check to see where my solutions lie, and you can test any point. Again, in general, testing 0, 0 is going to be the least amount of work. So we are going to test 0, 0. Okay, and so when I test 0, 0, I'm going to replace y with 0. And I am going to replace x with 0. And then plus 3. Okay, so left side stays the same. 0 is simplified. And then I have -2 times 0. Well, that's 0. And then plus 3 here. Okay, so as I'm looking at this, 0 is less than 3. I know that statement to be true. So what does that mean? So I tested 0, 0, and I found out that 0, 0 is a solution. So that means, again, all my solutions are going to lie on one side of the boundary or the other side of the boundary. They'll never be scattered. So since I tested 0, 0, I found out all my solution, or I found out 0, 0 is a solution. That means all of my solutions are on the side of 0, 0. So that means I want to shade the side with 0, 0 for this particular problem. So I'm going to go ahead and I'm going to do my best to shade it in. Okay, and then if I asked you for an ordered pair that is a solution to this, okay, besides 0, 0, obviously, you would give me any ordered pair in the highlighted region, but cannot be on the line. It's not on the line because I have an exclusive boundary line, which this is different from 2 because you could pick points on this line because that's an inclusive boundary line. Bold line, included in the solution set. Dash line, excluded from the solution set. All right, so now what we would like to do is just solve some word problems. Okay, so you receive a gift certificate to stock your fish tank with moonfish and minnows. Moonfish cost $2 each, and minnows cost $3 each. Letter A says that we would like to write an inequality in 2 variables to represent the number of moonfish and minnows you can buy without spending money over the amount of the gift card. So I want to only be able to use money that's on my gift card and not 1 cent extra. So let's start by defining our variables. Okay, and so in this situation, what's the things that's changing? It's going to be the number of moonfish or the number of minnows. Okay, so those are our variables, and they are totally interchangeable. I think I'm just going to say that, well, what comes first? Moonfish, I guess. So this would be number of moonfish. And then y can be number of minnows. Okay, so I know altogether I have $50 to spend. And if I don't want to spend 1 cent beyond that, we know that the amount I'm going to have at most is $50. So the amount of money I'm going to want to spend is going to have to be less than that. So those are the type of things that you want to be thinking about as you're doing these problems. Okay, let's represent the amount of money spent on moonfish and minnows, though. Okay, so if I want to figure out how much money spent on moonfish, I would take the number of moonfish, x, and I would multiply it by the price of moonfish, which it looks like is $2. So I have 2x. Okay, and then if I want to figure out my total amount of money, I'm going to add to it the money spent on minnows. So 2x plus, well, what's going to represent the money spent on minnows? I'm going to take the number of minnows I have together, y, and I'm going to multiply it by their price, which is 3. And altogether, I have $50 to spend. So if this is telling me how much money I'm spending on moonfish and minnows, what do we know about this amount of money in relation to 50? Well, we know it has to be less because I don't want to spend more than that amount that's on the gift card. But the question is, can it be less than, or is it going to be less than or equal to? And then this thing is, it says I don't want to spend money over the amount. So that means I can spend everything on the gift card. I just can't spend more than that amount. So it is going to be less than or equal to. Okay, lastly, we want to graph the inequality. And then we want to graph the inequality, then give 3 possible combinations. Okay, so let's go ahead and graph this. This particular problem is in standard form, so let's go ahead and find the x-intercept. Okay, the x-intercept is when y is equal to 0. So that means I'm going to have 2x is less than or equal to 50, which means x is less than or equal to 25. Okay, and so then the y-intercept is going to be when x is 0. And so then we are going to have 3y is less than or equal to 50. Divide by 3. Y is less than or equal to 50 divided by 3 is probably not going to come out to a nice, neat number, but that's all right. 16 and 2/3. So 16 and 2/3. So let's just say 16.7, give or take. Okay. Okay, so we have the x and y intercept, but what we want to do now is actually graph this. So you need to think about what values are you going to go up by. So here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 slots to work with on the x-axis, and I know I have to get up to 25. So if I went by 2s, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, well, that wouldn't get me to the number I need to get to, so I need to pick a higher value. So for example, 3. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. So that would get me to where I need to go. So I'm going to pick going by 3s, because if I go by 3s here, I can also go by 3s here, and because 16 and 0.7 would be incorporated in that. Okay, so let's go. So 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. Okay, and so now I just have to graph my x-intercept, okay? And again, this isn't going to be perfect, so, you know, we are just going to do the best we can. So it looks like that's going to be right about here if this is my x-axis, and this is my y-axis. So 16.7, again, not going to be perfect. It will be close. It'll be about almost halfway in here, not quite. Okay, bold line, so I can connect them with a bold, or or equal to, so I can connect that with a bold line because the solutions will be on the line. All right, and then I want to go ahead and test 0, 0. So 2 times 0 is 0, plus 3 times 0 is 0. So that's just 0 is less than or equal to 50, which is true. So that means I'm going to shade below. Okay, notice that I'm just going to kind of keep it in this positive area because there's no real, what do you call it? There's no real meaning behind having negative moonfish or negative minnows. So anything in that shaded region will work, kind of. Let's talk about why kind of. So for example, if I pick the ordered pair 0.5, 6.5, technically, mathematically speaking, that is a solution to this linear inequality. But does that really make sense? Does it make sense to buy a half of a moonfish and 6.5 minnows? Not really. My guess is you would be kind of disappointed if you went to the store and bought a minnow and you only received half of one, assuming that you were keeping those for pets. Maybe if you were using it for other methods, maybe not. Either way, the point being is that you really want to, in this certain situation, you really probably only want to pick whole number values that are in my solution set. So, for example, maybe like the ordered pair 6, 3. 6, 3 would be a solution, right? It makes sense of buying the proper amount of minnows, okay, and proper amount of moonfish, and I'm not buying halves of ones, okay. And so then you can really just pick anything in the shaded region, like maybe 12, 12 and 7, okay. What about this one? What about 0 minnows and 18 moonfish? 0 minnows and 18 moonfish. That's this point right here, which is on my line. Would that be a solution? In this situation, yes, it would be. This would be an example of me spending every single cent I have on just minnows. On just minnows because Y value is 18. But anything on the line is a solution, so that's what it would be. Okay, so good opportunity to pause the video and try the next one on your own. Check it with me when you are done. So I'm assuming that you've already tried this one on your own and you're just here to see how you did. Okay, so what this one says, it's pretty dated because CDs nor DVDs are a thing anymore, but when I was growing up, they were a really big deal. Okay, at a sale, CDs cost $8 each and DVDs cost $11 each. Okay, so CDs were just a way to listen to music digitally on a disc that you would put in your cards. DVDs were the same thing except for movies. And you have at most $88 to spend. Write a linear inequality in two variables to represent the number of CDs and the number of DVDs you can buy. Okay, so let's go ahead and say X can be number of CDs bought and Y can be number of DVDs bought. Okay, now it's not wrong if you flip those around. In fact, it could be very much correct. It just might look a little bit differently. We're just representing it differently. Just know that they're totally interchangeable here. Okay, and so now let's actually write the inequality. Okay, what I want to do is I want to take the money spent on CDs and DVDs. So $8 per CD, so $8 per CD, plus $11 per DVD. And I know it's going to be related to that $88. That's all I have to spend. We just have to think about what inequality sign am I going to use. Okay, so if I have to spend at most $88, I'm $88, that's the most I can spend. How much money am I going to be able to spend? Am I going to be able to spend $89, $90? No, because the most I have is $88. So that means all the money I can spend is $88 or less. So that's less than or equal to. Okay, let's go ahead and figure out how this is in standard form. So we're going to find the x-intercept. We're going to find the x-intercept by setting 8x is less than or equal to 88, because this means this is when y is 0. When y is 0, this goes away completely. Divide by 8 and say that x is less than or equal to 11. And the y-intercept is going to be 11y is less than or equal to 88. So y is less than or equal to 8. Okay, so when I number my axes, I need to be able to have it so they will incorporate 8 and 11. So this is going to go up to 10. So that tells me I cannot go by ones, because I'm going to get to, once I get to 10, that's going to be right here. I need to get 11 on. So we can go by 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, we can do the same thing this direction as well. Okay, x-intercept of 11. So here's 10. This is going to be exactly in between. Y-intercept of 8. Well, that has a spot for me, so that's good. It's going to be a bold line because if it's or equal to. Alrighty. And then I just need to figure out where I'm going to shade. Okay, so I'm going to test 0, 0. And when I test 0, 0, this is going to be, well, when I plug in 8 times 0, that's 0, plus 11 times 0, that's also 0. So I'm going to 0 is less than or equal to $88, which is true. So that means we're going to shade on the side that would include 0, 0, which is below. Okay, so then the last thing we need to do is give 3 possible combinations of CDs and DVDs, just so you know. This would be another example of where, for example, 4.5, 2.5 is mathematically a solution, but it doesn't make any sense in this problem. We're looking for whole numbers. You can't buy a half a CD if you were to take a CD and break it in half. It would not be usable anymore. So what we are going to do is we want to pick whole numbers that work. So for example, like 2, 1. That would be a solution. What about 8, 2? 8, 2. 8, 2 looks like it would be in there. That would work as well. All right, actually that's probably on the line. Which brings up a good point. Okay, so this is on the line. This would be a solution. How come? It's a bold line. That means the line is inclusive. So if I pick points on that line, it will be part of the solution set. Lastly, anything in the shaded region. So let's just go with 3, 4. For this particular part, you probably picked different ordered pairs for me, although it is worth bringing up that You definitely need whole numbers here because it wouldn't really make sense to have a half a CD or half of a DVD. Okay, otherwise that is the end of this section. You can go ahead and move on to the homework. Otherwise, I'll see you next time for 2.3.